iniziare e vorrei dare a nome di tutto il Dipartimento il benvenuto a Gigliola Staffilani, che abbiamo l'onore di avere oggi per il suo colloquio talk. E Gigliola è, come sapete, è lecturer della European Mathematical Society, quindi del 2018, quindi ringrazio anche la European Mathematical Society. E abbiamo anche l'onore di avere Roberto Natalini, biografo ufficiale di Gigliola Staffilani, e quindi lascio immediatamente a Roberto la parola per la presentazione dell'articolo. Grazie.
So that's a pleasure for me to introduce Gigliola Staffilani. Gigliola Staffilani is now Abby Rockefeller Mose Professor in MIT of Mathematics. She's the second full professor in mathematics. Woman in mathematics in MIT. She was born in Martinsicuro, in Abruzzo, and she got her laurea in Bologna, and then she she started her adventure in the United States, where she got a PhD in Chicago under the supervision of Thomas Koenig in 1995, and her interest in harmonic analysis, partial differential equation, and specifically about Courtwright degrees and Schrodinger equation. Today, also, we have seen this delicate introduction of Moravec's estimates, quite celebrated in dispersive, the topic of dispersive equations that were obtained by Gigliola some years ago with her collaborators, quite important collaborators, but she had a long time collaboration with Coriander, Kiel, Takaoka, and Terence Tao, the so-called I group they formed. And in 2014, she was admitted to American Academy of Art and Science, so that's a great honor. But she deserves completely this honor, I think. So that's all, and I think that you can enjoy this lecture.
Thank you, and thank you everybody for the opportunity to speak here. So now I apologize for the colors, but fortunately the purple is not going to appear very often, so you'll be okay. And I want to thank here, as you see, my institution, the National Science Foundation, and of course you, we have the European Mathematical Society. Okay, so yes, this is not working. So this talk, it's sort of a complement of what Nicola was talking about in his lectures, because I will be presenting the problem in the periodic case, where, as Nicola reminded you, there is no scattering. And in fact, I like to go through a bunch of different problems that have been considered in the last few years, because it touches upon a lot of different subjects. So a little bit of a summary of the talk. So, okay. So the introduction, and I wanted to explain a little bit what is the physics, at least in one direction, that brings in the Schrodinger equation. And then Strickland's estimates are extremely important, as you saw from Nicola's lectures. And in particular, in the periodic case, they are hard to obtain. The reason being that when you do Strickland's estimates on the plane, or in Rn in general, you do quite a lot of integration by parts. That's the way you obtain estimates for oscillatory integrals, so one that goes with lemma and things like that. And unfortunately, this is not possible in the periodic case, because instead of having a Fourier integral, you have a Fourier series. And when you have a series, you cannot integrate by part. And I will also, because there is not scattering, I will talk about what happens when t goes to infinity to a solution of a periodic equation. And this is linked, or at least one phenomenon that we can study is the so-called energy transfer, which is also connected to weak turbulence. And then I will switch gear, and you will see this colloquium talk, you will not have time to feel like you don't understand anything anymore, because I changed topic before you feel that way. So I will introduce a different kind of point of view of the same exact initial value problem, but in the Fourier space, and that will become an infinite dimension Hamiltonian. ever wondering whether the typical problems of theorems that you can prove in the finite dimension are also true in the infinite dimension? So there is quite an active area of research there, and we know very little in general, I guess. This brings me to the notion of Gibbs measure. And at the end, and I hope I have time, and I don't know if this is Russian style, I can go on forever, but I will stop. But I hope I can get to the non-squeezing theorem. This is one of those theorems that are already difficult to prove in a finite dimension Hamiltonian system. The original theorem is due to Gromov. And there are very recent and sort of not very satisfactory, satisfactory in the sense that there are just not that many. They are actually pretty beautiful theorems in the no squeezing for infinite dimension. And hopefully I will actually, if I don't have time, I would still like to jump to the open problems because there are a lot of young people here that might want to start working on that. Okay. So, like I said, I like to present this kind of topics when I give out a module because it really touches upon all sorts of different kind of subjects in mathematics. Obviously, harmonic and Fourier analysis. That's typical for this kind of problems. But what is kind of unexpected is the analytic number theory part. This is actually the contribution, very, very important contribution of Rugen in this topic that was brought in 1995, and then there is some much more recent advancement on that, 2014. So I would like to mention two things about that, hopefully. Of course, there is math physics, dynamical system involved, also probability, and like I mentioned, the non-squeezing symplectic geometry. So hopefully I get to do all of that, but especially because you have had already an introduction of the problem in general with Nicola, so you're probably familiar with many of these things. So as a sort of a guideline throughout the talk, the equation that I will be looking at is of this type. So this is the Schrodinger equation. The lambda here is to be plus or minus 1. Everything has been rescaled for the other constant that you can actually get it when you look at this equation coming from physics. So the lambda plus or minus 1 will give the character of defocusing and focusing to this problem. And there is an initial value problem, an initial value, because this is an initial value problem, that's du0x. This is imagine an initial profile, certain wave. The solutions of this dispersive equations are waves. And as I said at the beginning, I'm considering the periodic case because I find it to be, there are more problems to work on and a little bit different and sometimes strikingly different from what happens in the non-periodic case. And I'm going to denote that by saying that X is in the torus of dimension D. So that's what it means to be, you can interpret the periodicity as sitting on a torus. Now, there are two quantities that I always consider for this kind of equations. They come from physics, and it's the mass, and that's basically the L2 norm square, and the Hamiltonian of energy, if you like. This is the kinetic energy, it's the gradient, and this is the potential energy. Here I'm only looking at the cubic NLS. People say that's the most physical one, but also because I need to give you some specific numbers and exponents, and I don't want to generalize in the full, but of course there are corresponding results to what I present for our nonlinearity, for our dimensions, and so on. Okay, so now that I've introduced the problem, let me just tell you at least one example where it comes from. So the NLS nonlinear Schrodinger equation is very much linked to a phenomenon called Bose-Einstein condensate. So the Bose-Einstein condensate is something that happens when you have a very, let's think of a container or a potential that keeps particles together, and these particles are the gas is very rarefied, so there are very few particles that you are considering, but there's still, a very large number. And if you have a gas and you are in higher temperature, well, the dynamics of these particles can be studied by looking at the physics of billiard balls. But that's not the case when you start lowering the temperature. And in fact, the best way to sort of see that is instead of particles like a position and velocity, let's think of them as little wave packets. So these are little wave packets here. And if the distance between the wave packets and the wavelength within the wave packets are related so that the distance is much larger than the wavelength, then they basically don't interact that much. But as the temperature lowers, then there is start being some interaction, as you see here in my picture. And then as the temperature goes to the zero, there is this formation of this giant wave. And basically what happens is that these wave packets that sort of at the beginning are interacted without too much interaction with itself, that really lose their independence in a sense, that's how people like to say, they become a big blob right here. So this is the Bose-Einstein condensate. By the way, this has been proved in physics experimentally. People got Nobel Prize and all of that. So let me now tell you a little bit the mathematics behind it. So I am going to spare you the technicalities because even just writing this thing down is very complicated. But let me just tell you what happens. So one way of representing this object, which is a cartoon for me, is through the so-called BBGKY hierarchy. So there's going to be an infinite number of equations interacting with each other that tells me how these wave packets interact with each other in the experiment as the temperature goes to zero or as the number of particles goes to infinity. Those two things are kind of related. And then you have to take a limit from this guy. And let's say in this way I'm going to take the limit as the number of particles to infinity. You obtain a so-called Gross-Petagevsky hierarchy. Now this process of taking the limit in dimension 3 was only accomplished in around 2007, 2008. And the interesting thing that was done, maybe I have some names on the next slides, yes, was original work postponed, but then really Erdős, Schlein, and Yao, and they claimed that their one main important element of their proof was some kind of Swikart's estimates. And then I worked on this with Kirkpatrick and Schlein, Benjamin Schlein in the periodic case, and there are other groups here working. But just to tell you what the relationship between this Gross-Petagevsky hierarchy and the Schrodinger equation, let me just simplify things for you. So let's fix a k, and this vector xk, which is x1 to xk, each one of these guys represented the position, and here think about R3 if you want. And this gamma 0k is an initial data for the large Gross-Petagevsky hierarchy, which I'm not writing for you. You don't need to know what that is. So this is an initial data, and the way I wrote it is so-called in a factorized way. So this is the product of basically functions. So that's u0 xj, and then u0 bar, that's the complex conjugate xj prime. So this is supposed to be some density, but never mind that. But it is written in a factorized way. These are waves, initial waves, if you like. Same function, u0, u0 bar. And then if you crank the machine and you write the solution of the Gross-Petagevsky, which we now know exists, is unique, and so on, thanks to the work Erdős, Schlein, and Yao, then we found that actually the solution, now you see the T here, so this is the solution of the Gross-Petagevsky, it's the product of certain functions u, where the relationship between u0 and u is that u solves the nonlinear Schrodinger equation, where u0 is the initial data. So that's what the link is. Okay, so I wanted to just mention one thing about the Gross-Petagevsky, which I found interesting. So if we think about just the Schrodinger equation in one dimension for now, then maybe many of you know that this is an integrable system. So there are not just the two conservation law, mass and energy, but there are infinitely many of them. And in fact, they are written like integrals, where the first piece is a derivative, order s, where x is any number, natural number. In fact, s equals 0 would be the mass, s equals 1 would be the Hamiltonian, but then there is also for s equals 2 and so on, infinitely many of them. And so this is an expression of the integrability. It's also lax pair, inverse scattering. These are all connected, and it's all part of being an integral system. So with my, actually this is a team of women, so Dana Mendelsohn is my graduate student, and Namhot and Pavlovich are all collaborators of mine. So we wonder whether this integrability structure is also true from the Gross-Petagevsky. So that's this infinite dimension big equation that's linked to the NLS via the way I told you before. And it was interesting to know there was nothing in the literature at all. And so we worked on it for quite a long time because our original goal was to look for Laplace pairs or for the geometric structure that really gives you the integrability. There's a very rich geometric structure behind this equation. We were looking for something like that, which is a lot more complicated, but nevertheless we were able to prove that at least there are infinite remaining conservation law also for the Gross-Pitariesky. And we are now working in collaboration with a student of Pavlovich to prove also more structure in it, more geometric structure in it. But it basically was interesting to know that there was nothing connected, and I'm not going to talk about that, but proving that there are also here conservation law is important in order also to describe certain Gibbs measures that I will mention to you at the end. But it's not just an isolated point that's important. Now, let's talk about what Postman's. All the young people here that were in the lectures of Nicola already know that, but just let me recall. So this is the initial value problem, and instead of looking at it as an equation finding solution in the classical sense, for which it means that u has to have at least two derivatives with respect to x, one derivative with respect to t, instead of interpreting it in the classical way, which brings us outside the quantities that are relevant for the problem, such as the mass and the energy. The energy only has one derivative, and here you ask it two, so that doesn't seem to be the right way to approach it. So we're going to change this into the integral equation, which is this. And so u is equal to the linear evolution. This is the Schrodinger group is acting on the initial data, and then of course you have to take care of the nonlinearity. That's how it's written. This is via the Duhamel principle. And then we try to look at this formulation here. Of course, I'm writing u in terms of u, so I'm not giving you an explicit expression for u itself. But we note that if we think of the right-hand side as an operator of u, then a fixed point of this operator will be giving me exactly this relationship, which then in turn tells me that I have a solution. So the goal is to find a fixed point for the operator that is here on the right-hand side, where u is the input, and whatever you see the expression here is the output. So when you want to use a fixed point, well, you need to have first a space where the fixed point can be applied, and then of course estimates that tell you that a fixed point exists, such for example contraction method, if you like. So to identify the space where this fixed point might happen, what you do is, at least one way of doing this, is to look at the linear part, which actually is explicit. You have an explicit formula for it, you will see in a second. And then try to prove as many estimates as possible for this, in particular multilinear estimates, because eventually you're going to have to look at this multilinear expression here. And then based on those estimates, try to figure out what's the space where the whole thing, including the nonlinear part, which you hope is a perturbation of the linear one, can be handled. Okay, so based on this principle, we're just going to concentrate on this first. And this is the linear solution, which means that solves this problem. This is my initial data, this is just the linear operator. Now, you can write it explicitly. I'm going to show you right here, in fact. Here it is. So you might have seen it in the continuous case, so in Rn or Rd. So let me write it for you in the periodic case. So the way you do it, let me just step back 1 second. The way you get the explicit expression for V is, or for STU0, is take Fourier transform with respect to space only. You obtain an ODE, and then you solve the ODE. Okay, now in the periodic case, you have Fourier series. So we'll end up like that. So this part, just the u dot hat n is the Fourier coefficient to u dot n, that u dot, which is initial data. If you ignore this piece, you will just reconstruct the function, so you will just go back to u naught. But this is what happens when you have the fact that you have a Schrodinger operator. Now, the Schrodinger has two derivatives with respect to space, so that's why you have n1 square and 2 square. So I'm writing this down in 2 dimensions for simplicity. So n is z2, so it's one of the lattice points. And this alpha 1 and alpha 2 are positive quantities which are related to the periods in the two different directions. And actually, the relationship between alpha 1 and alpha 2 is very important for a reason that I will tell you in a moment. So if alpha 1 and alpha 2 are just rational numbers, actually you can also say if alpha 1 over alpha 2 is a rational number, then we call that a rational torus. But if one of the alphas is irrational, then we call the torus an irrational torus. Okay, there is a definition for the rationality of the torus in higher dimension, but I'm not going to go to that. And believe it or not, this makes a difference. Intuitively, that also seems reasonable, because if you imagine looking at a wave with the periodic boundary conditions, and you hit the boundary and you have a rational torus, you expect the more the bouncing back affects the entering part as well. But if you are in the irrational case, you will have a little bit more room to move around. So in theory, it looks like the irrational case should be, or the dynamics in the irrational case should be more smoother in some sense, or the wave itself will have more time to maneuver and hence feeling less the effect of the boundary. But this was kind of like, intuitively. In practice, actually, as I will show you, the first estimates were available here, but not here at all. So let me tell you a little bit about that. So the first estimates on this were by Bourgain in around the mid-90s or so. And if you know what, if you know the exponents of the Strickler's estimates, well, taking the L4 in time and L4 in space, so a 4-4 is an admissible couple in R2, except that in R2 here you will not get the H epsilon space, so you don't lose any derivative, you only have an L2 norm in here, which is the mass, which is exactly how we want to do things. But in the periodic case, you have a loss, a very little loss of epsilon right here. Another thing that you might be surprised is, why do I put here torus again? I mean, I'm looking at L4 in time and L4 in space. Well, an interesting fact is that when you have a rational torus, immediately, you can see from the formula, you can see that if you have a rational torus, so alpha 1 and alpha 2 are fractions, well, you also have periodicity with respect to time. And that does not happen if you have an irrational torus, okay? So that's the reason why I put here torus. And this is an explicit example of the fact that there is no scattering. This is periodic in time. There is no decay in time at all, which is what happens when, or the dispersion, which is similar to scattering anyway. So there are many different things besides the shape of the solution. There are facts that you have to be careful about. Anyway, so the first thing we notice is that now this solution is also periodic in time, and that's why I put tau here, or the circle if you like. Okay, so then I'm not going to do the proof, but actually the proof that Bourgain does is not very hard to show this fact. If you wanted to practice, what you do is, from an L4, write the L4 as a product of STU0 times STU0 in L2. That would be the square of this guy. And now you are in L2, you can use Plancherel, then you take Fourier transform everywhere. And now you have a convolution of these two linear solutions. Each one of them in Fourier transform lives on the parabola. That's where the Schrodinger lives, in the frequency space. And then you do some Cauchy-Schwarz, and at the end of the day, you lose something by having to put there a measure of a certain set of lattice points. The set of lattice points is this. So n is a lattice point such that alpha 1 and 1 square plus alpha 2 and 2 square equals r. Put an r square here if you like, okay, a radius. So if you think of alpha 1 and alpha 2 to be just 1, you have a perfect circle of radius r, like that. And you want to know how many lattice points fits exactly on this circle. And this is actually a problem in number theory, which is not really solved by counting the lattice point. It's more solved by how many solutions this kind of equation, Diophantine, well, no, this is not Diophantine, it's just equations with all numbers being natural numbers are there. And there is a Gauss lemma which tells you exactly how many of these solutions, how many of these n's you can have to solve this equation, like with the square here. And the estimate is very sharp one. It's an exponential of log r of log r, whatever, but this is less than r to the epsilon, and that's where the epsilon comes in. So this is a very different kind of proof than the one you have when you do harmonic analysis in R2. So what I want to say is that in this particular proof of Bourgain, analytic number theory, it's feeding into harmonic analysis. It's telling you results that usually you get in harmonic analysis. Okay, so for many years, that was it. We all expect that this should be true in any generic torus, but really the proof could not be generalized at all. So then in 2014, Bourgain again and Demeter proved the whole, I only report here the dimension 2, but there is a whole theorem in higher dimension and so on. And it says that in any torus, so now because I'm taking any torus here, I cannot say anymore that's periodic in time, so I have to cut with respect to a finite interval. It's not important 0, 1. I will actually talk about this in one of my lectures. I will give the proof of both the proof of Bourgain and the proof of this fact. So they proved that the same estimates hold, but the proof is completely different. It has nothing to do with number theory, and it's based on the so-called L2 decoupling theorem. I will talk about that in my lecture as well, and also holds for higher dimension. Now, I have to say that just Strickard's estimates are not enough. Like if you just have this, you are not able to go back and prove that there is a fixed point for that operator that I mentioned before. You need something a little bit sharper. You need to understand what happens when you interact a function or a solution that lives in high frequencies with a solution that lives in very low frequency. So that's what you do in the so-called bilinear estimates, which was done by Bourgain also in the rational case, and I worked on it with one of my students at postdocs, and we proved now also in the irrational case. And then I also want to mention that this idea of thinking that if you are in the irrational torus, estimates should actually be better because you have a little bit more room, don't bounce directly back on yourself. That was actually proved to be true in a certain sense because Germain, you then show that the length of time for which you can actually prove the Strickard's is longer if you have an irrational torus rather than a rational one. So there is this idea that you have less interaction is correct. But what I found to be fascinating is that now using the harmonic analysis that comes from proving this L2 decoupling theorem, which was a very old conjecture for a very long time. So the harmonic analysis that is used there is now used in order to prove big open conjecture in analytic number theory. An example of that is the recent work of Bourgain and Demeter group, who show prove the conjecture, so mean value theorem of Vinogradov, which is related to finding solution of certain equations. So at the moment, the harmonic analysis is actually feeding the results to analytic number theory. But this is still due to the fact that Bourgain really understood the connection between the two. Okay, so now that's becoming harder, we should switch gear. So by using the bilinear Strickard's and the Strickard's, now we know that for any torus, we have at least a local solution of this problem. And if you are in the defocusing case, you can use the conservation law given by the energy. You can certainly claim that if you have an initial profile which is smooth enough, in particular S greater or equal than 1, that's the level where the energy lives, then there is a global solution. You can actually go a little bit below 1 by using the almost conservation law, but I'm not going to talk about that. So now we know in particular that there is, for any smooth initial data, there is a smooth solution for all times. What we don't know is what happens as t goes to infinity. In the equivalent problem, maybe I'll say it later. In fact, let me. So in the problem, when you are, instead of the torus of dimension 2, you are on the plane, we recently learned what the conclusion in that case is, thanks to the work of Dodson, and it is scattering, what Nicola was talking about. But in the periodic case, there is no scattering. So what happens to the solution? I mean, we know that on the plane, I approach something linear. But what happens if instead you are in the periodic condition? So one phenomenon that you might try to prove that exists or that happens is the so-called transfer of energy. So let me try to explain a little bit what that is. And I wanted to mention before everything that the results that we know for this particular problem are at all not sharp. So it would be really nice to have people come with new idea and prove something sharper than what we have. So let me describe what we have, and then you can decide for yourself if you want to embark on working on this a little bit more. So the kind of problem we wanted to solve is the following. So let me look at everything in the frequency space now. It's interesting, like in these kind of problems, you really have to keep track of both situations, the physical space and the frequency space. But here the picture is in the frequency space. So I'm looking at the Fourier coefficients. And this U0 is the initial data. I'm taking the Fourier coefficient at C, and I'm taking the absolute value of it, and then I'm squaring it. And here I'm doing actually a continuous picture, although really, because C is in Z or Z2, whatever, this should be just dots, but never mind. So this is the profile of the Fourier coefficient. This is time 0. So the question is, when time evolves, do we get, like this is concentrated at basically very low frequency. Does it happen that this green blob is going to move to very, very high frequency? So it's this motion from low to high frequency. This is also called forward cascade. It's also whip turbulence kind of idea. So is this happening? Well, this is not at all triviality to prove, because the problem has a lot of constraints. So for example, if you look at the area of the subgraph, that means you take the integral of this guy. By Planck-Charel, that's really looking at the mass. And we know that the mass is conserved. So we know that even if there is this motion from low to high, has to happen so that this subgraph, the area of the subgraph is constant. So it cannot be, and I'm not even putting in the fact that also the energy is conserved, which gives even more constraints. So it's not like one can do wild things in here. But one way that was proposed in order to understand whether there is a motion of this object from low to high is to hit it with the weight. This is the usual Sobolev weight, and then integrate it. So if you hit with the weight and there is more stuff for higher weight, then you will feel it as t goes to infinity. And if you integrate, that happens to be exactly the HS norm, so maybe that's an object that you can study. So this is, maybe you heard, polynomial bounds or HS norm or Sobolev HS norms or Sobolev norms for solution of nonlinear Schrodinger equation. That's why we are interested in that. The H1 in the defocussing case, for example, we know already that it's bounded. That's because of the energy. But if S is greater than 1, we really don't know anything, except in 2 cases, which I will mention in a second. So that's our goal, study these HS norms. So complete integrability, like the example that I gave before, the one-dimension cubic NLS, will prevent, of course, moving of energy transfer from low to high. Why? Because we know that there are all these integrals that have higher and higher order derivatives, and we can recombine them so that we have a bound for any HS norm. So complete integrability, it does not give you scattering, no even the periodic, so it does not give you energy transfer, no even the periodic case. Another situation that it's interesting to study is what happens if instead of the periodic case, I have actually my equation in Rn. In this case, let's think about R2. As I said before, recently, in fact, a few years ago, Dodson, like 3 or 4 or something, Dodson proved that there is scattering. So just like Nicola said, there is a U plus and U minus in HS, any S greater than 1, such that as t goes to infinity, ut approaches this linear, so it's a linear evolution, this U plus U minus, as t goes to plus or minus infinity. Then of course, if you approach something linear, then you know in any case that the HS norm of the linear problem is equal the HS norm of the initial data, if you want. That's because it's just e to the I, the difference between this guy and this guy is e to the I something, and then you put that to value, kill it. So HS norm are the same. So if this guy approaches the linear problem, then, and this linear part has the just no bound, and then you have a bound everywhere. So in R2 it's not going to happen that there is this transfer of energy. So now let me tell you what the results are for the problem. So when you have this kind of problem, there are two approaches that you can try to concentrate your effort on. The first one is, well, if there is this growth of Sobolev norm, which is will imply that there is a transfer of energy, then how much can it grow in time? So these are upper bounds. And this is just, give me any solution, I can tell you that cannot grow more than a certain amount in time. Then there is the other approach, which is it there a solution that actually grows? So then that's a constructive part, and that's sort of something that comes from below. So let me tell you two examples of problems that or results. So the first one, here's Bourgain originally, and a student of mine worked on it, and this is in the torus of dimension 2, and the original proof was only for the rational case, because it was based on Strickhart's, but now went back to the work of Bourgain, and it works. I think if you know the new Strickhart's and linear Strickhart's, you can extend that to many torus. And it says that the growth cannot be more than a polynomial of degree s, plus something anyway. The fact is that this is not sharp at all. I'm going to talk about this in my lectures today, tomorrow. Improving in here in the order of the polynomial bound here would be great. And another result, which is something from above, says the following. So give me a S, should be 1 here actually, not 0. Give me an S, that's the order of regularity. Give me a small delta and give me a large K. Then I can construct for you a solution, but only in the rational case, the torus is rational. Can construct for you a solution such that if you wait long enough, capital T, and that's a very long time, it will become, so you start like less than delta, it will become as larger K. There are many drawbacks of these results. First, the fact that only true for rational case. The construction is done for rational case. And in fact, I have a recent result with a student, a postdoc of mine, Bobby Wilson, and we proved that in the irrational case, this dynamic is not happening. So it's really not there. And I will talk about this in my lectures as well. Okay, that's first drawback, but in the irrational case, whatever dynamic we show here is not happening. And also the drawback is the fact that I really cannot tell you what happens after capital T. It might get small again. You cannot prove that. There is also a similar result, similar in terms of spirits, not definitely on proof. And this is by Carl and Faour, also for the rational case. And also the result of Carl and Faour does not extend in the rational, and we prove that. And I will talk about that in the lecture. So it's very, as you can see, it's very limited. Oh, here we go, I will say it. So in the, for irrational tori, Udeng and Germain, or Udeng by himself, proved that the polynomial bounds are actually better, which is consistent with the fact that the Strickhart's live for a longer time. So everything, in fact, it is better for the irrational, generically speaking. And then, like I said here, this is work with Bobby Wilson and myself. We proved that the dynamics that we have both in the example, the construction that I gave before, and the result of Carter was not going to happen. So it's a very rigid structure. Okay, so let me give you an idea how you prove the constructive, the existence of this solution that actually grow on a certain time. And I will be very brief. So the first one is that we have, I'm only showing that there is a solution that grows. Obviously, this is not true that every solution grows. So I have a little bit of freedom in figuring out what is the ansatz that I want to put in. So I'm looking for a solution that looks like this. Basically, the whole dynamics is going to give how this Fourier coefficients, if you like, behave. So my whole system is reduced to finding the system for the A and T, which is an infinite system with infinite many type of interactions of n's frequency from any size to any size, like infinite small, infinite large. So that's too much of a big system to study from a dynamical system point of view. So you start making a reduction. The first reduction is you expect the growth to come from resonance. We know that from physics, so it seems that only the resonance frequency should be considered. That simplifies a lot, but it's still infinite dimension. Then we construct a set of frequencies which is close under resonancy, but it's a finite dimension. And again, I will explain this, I will give a whole lecture on this in my future lectures here. And so by doing a sort of reductions, we end up with what we call a toy model, which looks like this, where now the interactions are only nearest neighborhood. So we took away a lot of stuff. This is not the original problem we started with, but we can say that it's close enough. And if I prove that this grows, then because the error that I make between this model and the original one is very small, then this will dictate the growth, because I'm looking about the growth. So now I will, so what's the idea here? Maybe it's mine. No, it's not mine. Sorry, it wasn't enough. So how do you, basically what do we have to prove? We have to prove that if we are very low, our dynamics pushes, as long as we are waiting for a long time, pushes us high. So this J now represents low frequency and high frequency in a certain sense. The rigidity of the problem that I expressed before in terms of the conservation of the mass, conservation of the energy, it translates in a sense in our dynamical system with the fact that if we start exactly on this frequency or exactly on this kind of tori, if you want, you stop there. You don't move at all. So you have to be careful in avoiding these trapping areas where you will never get out of it. And the theorem says that you can. I'm not going to give you the details, but it's a very much dynamical system type of theorem. And I have to say that neither of myself and my teammate were experts in dynamical system. So then later on, our work was taken by, was reviewed by Guardia Kaloshin and Guardia House of Purchase, here actually, with the area anyway. So they worked on this from the dynamical system point of view in a much better way than we could do. And I just want to mention some work of Gerard Grelier. They took a different kind of equation, but they obtained many more results than we did. And I wanted to mention the work of Zaher Hani, Posador, Tsetko, and Nicola here, who actually proved, they don't just prove that they grow and they don't know what happens afterwards. They actually proved that solution of, in this kind of manifold, so the manifold, X variable is in R cross T2, so it's not just periodic, there is a little bit of a long dimension that you can use. And they actually prove growth in time. And then the Fauscherman and Hani large box limit and so on, and then here I have some more. If you want, I can give you more references. But what I want to say is that we don't know much about this problem in general. Okay, so now, how much time do I have? Because I can stop anymore.
10 minutes.
10 minutes, okay, good. So, yeah, all right. So now I wanted to start in a different direction a little bit. So I wanted to reinterpret the NLS initial value problem as an infinite dimension Hamiltonian system. But first I wanted to tell you something finite dimension Hamiltonian system, which in this case is completely trivial, but I just wanted to say. So this is the way we usually write it. This is the finite dimension because n goes from 1 to d. We have the variable an, the variable bn, and this is the flow. And what we know is that, for example, this flow preserves the volume. So if you take a set A in R2D, 2D because there are this AD, take the volume of A, and then you prove very easily that the volume of the evolution of A at any time is the same as the volume of A. That's really due to the fact of Liouville theorem, because we have a Hamiltonian here, so you can prove very easily that. So you can immediately claim that yes, you have the volume measure which is invariant, but also you have another measure which is invariant. And this is by taking the volume that we know already is invariant and then multiplying it by e to the minus the Hamiltonian, which is also invariant because it's the Hamiltonian system. Here I put 1 over z just because I want to make this a probability measure. I just want to normalize it. This is called the Gibbs measure, and just from what I explained, the measure of a set A is the same as the measure of any evolution of any time of the set A itself. So this is all clear and easy. So now let me go to the nonlinear Schrodinger equation. For the moment, ignore this blue stuff, or green, whatever. So just look at the yellow. So if you take U and you take Fourier transfer of it, then you can write the real part and the imaginary part. And the interesting fact is that the AN and BN, which are infinite vectors because now n is in Z2, actually satisfy a system which looks exactly like an Hamiltonian system, except for the fact that n is now in Z2, where H, forget the W for a moment, where H is the Hamiltonian that I wrote before. So this is clear and it's easy to do. Now the question becomes, am I able to define a measure which is reminiscent of the Gibbs measure and define a dimension? That's a kind of interesting question because it would describe something of the dynamics of the physics, okay, of the problem. So roughly speaking, that will look like e to the Hamiltonian, then some kind of volume measure. Of course, the volume here is infinite because we have infinite, n is in Z2. So you cannot just do that. It doesn't make any sense whatsoever. Well, some probabilists of not small caliber, Leibowitz, Rosen-Spear in 1D, and Glim and Jaffe in 2D and 3D, prove that this can be done in some cases. So let me explain the situation that we have, which is torus of dimension 2. And I'm not going to go further on that. Well, they prove that, for example, if here we just have the usual cubic nonlinearity, that's not going to work. There is some kind of normalization we have to do. And that's called weak order. So you weak order the Hamiltonian actually, and then from that weak order Hamiltonian, you derive what's the right nonlinearity to put there. So for the original problem that I wrote, you cannot do what I was trying to do, the Gibbs measure. You have to renormalize in a sense. You renormalize, and let me call n of u to be the normalization. I'll tell you in a moment what the weak order does to the nonlinearity. It still looks like cubic, but some of the frequencies are removed. But then now with this n, or with the weak order h, you can actually write this, and you can actually prove that there is a measure like this that makes sense. Later on, what Bourgain did was to show that this measure is invariant. So let me just, maybe this is my last kind of slide or so. So as for the existence of this measure, well, you first have to renormalize, but the way this, you make sense of it is by taking the linear part of the Hamiltonian and make the so-called Gaussian measure. Many of you probably already did that construction. So you write the Gaussian measure. That basically takes care of the linear part of the Hamiltonian. But you had to do some calculation to show that if you wanted to behave good, in a good way, well, then the support of the measure in 2 dimension here is in h minus epsilon. So it's very rough support, h minus epsilon. And then you make sense, once you have the Gaussian measure, you prove that this object here, I put the 2 dots here because this has been renormalized, that's the weak order. Then you prove that this is integrable with respect to Gaussian measure, and so this makes sense. Now, what Bourgain wanted to prove was that this measure, the d mu, was invariant. By the way, the 1 over z again is to normalize it. And so to make it a probability measure. Now, the question of invariance is very complicated. First of all, because you have to prove that in the support of the measure. The support is h minus epsilon. And now, if you remember, the flow of this problem existed in h epsilon, because in the Sobolev, in the Strickhart's norm, you use an epsilon. So the support is h minus epsilon. The well-Posners in a deterministic way is in h epsilon. So there is no even flow to talk about, you know, the invariance of the flow. And that's the big contribution of Bourgain, is to make sure that you could prove that there is a flow. And not just that there is a flow, he was able to first prove that there is a flow locally, and then he was able to use the invariance of the measure to go from local to global in lieu of a conservation law, for example. And the final theorem says, well, take the dimension 2. By the way, he did it only in the rational case again. And with my collaborators now, we prove that this is true also in the irrational, but it's not that trivial. Anyway, So the theorem goes as follows. You can find a set of full measure in the support of the measure itself, such that for any initial data there is a global flow, and that flow maintains the measure invariance. So to conclude, I just want to show you a calculation. Why does it work? I mean, what did it do in order to prove that there is a flow in here? Because deterministically it's not possible. Well, this is what it does. So this is the initial data written in a way that tells you that you are in the support of the measure. In fact, if you look at the HS, so this is Gn omega, these are just, imagine plus or minus one randomly picked. So this is independent, identically distributed Gaussian complex random variables. That's this guy here. And then you divide by, this is the, if you like, n non-zero, or 1 plus n square roots, if you like. That's the Japanese bracket. And then e to the I and x. So this is the initial data. And this, if you do the calculation, is in h minus epsilon. You can do that. There is this underground, the background probability space. And then at some point, when he does his calculation, he has to, well, first of all, he's not looking for the solution of u itself for the problem. What he does, he looks at u minus the Schrodinger linear evolution of this initial data. And I don't know how he thought that that was possible to prove, but what it proves is that u minus the linear evolution of this is much better. In fact, it jumps up in h epsilon instead of staying in h minus epsilon. So it takes, the linear part is bad. And you will understand why in a second. So if you do that, then the nonlinearity, so let me just write it here. So instead of u, you look at w, which is u minus the linear evolution, that u0 that you see there. And then when you find what kind of equation w satisfy, you see that it's, again, the Schrodinger. But now there is a nonlinearity, that's the n. And here there is w plus st u naught. That's what it satisfies. And now when you imagine this to be a cubic, so you have a different kind of interaction. You have w cubed. That's, if I'm thinking of w to be smoother, that's something I can handle by streetcars. And then there is a bunch of stuff. So in particular, there is this guy multiplied 3 times. And why is it better to have a 3 times multiplication of this guy versus just one of them? It's better because when you multiply 3 times, you have independence. And then you can, if you don't multiply with anything, you cannot use the independence. So let me just go ahead and show you that calculation and I conclude. So when you do there's a bunch of stuff. Here I'm going to give you an example. At some point you have to estimate little ln, little lm. This is because it's also periodic in time. Remember, we are in the rational case. Expressions such as this. This is nothing else than the Fourier, the convolution, the Fourier transform of linear solutions of these guys. So you have, so this is a convolution because I'm taking n1, n2, and 3. This is the convolution relationship. And then here is the fact that I'm taking solution of the Schrodinger equation. And n1 and 3 not equal and 2 is exactly what weak ordering does for you. So it removes certain frequency. That comes from the normalization of the equation itself. And then when you go ahead and do this calculation, well, if you are naive, so you're looking, I wanted to estimate that, I just wrote it for you. I have a sum in n and m, and then the absolute value square of this expression. And if you do what Bourgain does in proving streetcars, you want to put the square inside, that means you do Cauchy-Schwarz, you lose a certain measure of a set. I'm not going to, but anyway, here there is some loss of derivative. Measure of sets in the Fourier coefficient means that you lose derivative in space. So you lose, there's nothing you can do about that. But we have no use at all, we killed, in fact, any kind of randomness here by putting the absolute value, which is something we don't want to do. So we go back, we write again the same expression, then at this point, I'm going to use a large deviation estimate that tells me that I can estimate the absolute value of this expression with the L2 norm of that. And when I write down this L2 norm, well, this delta comes from the fact that you have a little, not at all the loss of derivative, but some delta, which means that instead of doing everything in the set omega, you have to restrict the probability set a tiny bit. But anyway, don't worry about that. And then you write it down, the whole expression, and now here you have this integral in omega, but there are the constraints that which comes from weak ordering that tells you that a lot of frequencies are not equal to each other. So basically everything collapses due to independence and the fact that these frequencies are not equal to each other, and you get that. So now if you compare this part with this part, you see that here you had a loss, and here you don't. This delta is a constant, it's just how much you have to restrict omega, and that's why it gains. So I'm gonna. If you want to know about the non-squeezing, ask me, but I don't want to keep you here more. Thank you.
Okay, thank you, Gigliola, for this brilliant
Some lines.
lecture. And is there any question?
Can you tell us something more about the rational case that you mentioned before?
About this particular problem or in general?
No, the one by Bourgain.
Oh yes. So if you go through the calculation of this Bourgain's analysis, and good luck those people who want to read the paper because it leaves all the things out. But you can see that he does a lot of counting, which is kind of like this. So if you are not in the rational case, you cannot use this result. So when we are working now with my collaborators, so the procedure is similar. I mean, it's the same kind of calculation you have to do, but you cannot count that easily. But what we do is instead we use Diophantine condition in the counting part of the problem. And the interesting part is that the result is slightly weaker than what he gets, in the sense that he can prove that you are smoother, you are above, now you are in H epsilon, but he could prove that our epsilon was a certain small fraction, and our fraction is a little bit smaller than that. So, yeah, maybe there is other ways where you can gain, but at least we can close now.
Not only in dimension 2, but even higher.
Higher, it's so in higher dimension, the problem here is that the measure itself is defined an even rougher space. So for dimension 3, for example, it's h minus a half minus epsilon. So it's so rough that there is nothing really that you can do at that level. So dimension 2 is exactly at the borderline of being bad but not too bad. Yeah.
Why don't you finish the lecture? I think that is the squeezing is the open problems.
Oh, the open problems, yes, okay. At least the open problems, okay. The squeezing is, okay. It's the fact that tells you that there are a few cases which you can. So the squeezing, for those people who don't know what it is, but basically says that if you have one of these nice Hamiltonian flows, you cannot squeeze a ball in a cylinder which has the diameter smaller than or the radius smaller than the ball itself. That was proved by Gromov. And so now we have this infinite dimension Hamiltonian system. Can we say something like that? And well, in principle, Cookson, if you want to read his work, that's the first to start, things to start first. But he proves that that's possible only if your flow is a compact perturbation of the linear one, which is not the case for KDB, it's not the case for Schrodinger, it's not the case for many wave equations. So he has to cook up different kind of equations which are not natural to apply his theory. So there are few results that I know in which you can actually prove no squeezing. The first one is also due to Bourgain, is the NLS in 1D cubic. The L2 is the symplectic space. Then there is a work that we did for KDB in H minus epsilon. This is the symplectic space case. But while this proof was kind of direct and not too hard, our proof is, I'm still not happy about this because I felt like I was trying to climb on a mirror. Okay, so we did it, but not in a natural way, so it would be great to have another kind of proof. And my student, Diana Manderson, the interesting part is that she was working on a flow which actually was almost surely defined, in the sense that there was some probability in there, and she got some results, and recently killed the Visan, but this is in R2, it's not in the periodic case. So just to say that there is a lot, I mean, we would love to have a proof that works for all these examples as example, this more general proof, but we don't have it. So let me just go to the open problems. So understanding the Strickard's estimate more directly. So I told you this is a corollary, and I will explain in my lecture, is a corollary or a much more complicated theorem, the L2 decoupling. And the Strickard's estimate is kind of like a corollary of that. It's kind of when you try to shoot a bird with a cannon, you probably kill it, but maybe you didn't need all the cannon. You'd be fine with just a gun. But, so we would like to have something a little bit more approachable. Improving theorem with turbulence, I told you already. I mean, we have some upper bounds are not sharp, some lower bounds are not so good, so it would be good to have more on that. Of course, understanding a ergodic structure associated to this infinite dimensional unit flows is more a probabilistic point of view. And then there is some work which I'm not sure is known very much in the community, in the dispersal in PDE, by Chatterjee and Kirkpatrick. What they do is they discretize the equation in the physical space, and then they put quite a lot of interesting phase transition and other kind of more probabilistic theorems. And of course, to conclude, is finding more robust arguments to approach this non-squeezing theorem, which is more on the subjective stuff. And I have not seen much progress in there, but I really feel like it's a good area to look at things. And that's it. Now I'm done.
Thank you again. I think we can stop here. I don't know. We have lunch now.
Lunch break?
Yeah, lunch break now, and this afternoon and tomorrow morning we have the lectures of the course.
And you can ask me things in between breaks and everything. Thank you.
Okay.